We're going to come back to just a few more concepts and the introduction to the physiology of perception. Now, it's been a bit much, and I'm going to repeat a little bit right now to put us back where we were, that we are feeling that touch. And so that touch receptor is receiving stimulation. It's receiving enough stimulation that it sends an action potential, that electrical signal that goes down the axon. We can see the myelin sheath there, speeding that along, making that more efficient. That action potential goes from the outside of the soma at that axon hillock all the way down the axon to the synapse, where now those terminal buttons that come off at the end of the axon, they're going to meet up with the postsynaptic neuron. And when I say meet up, there's actually a small microscopic gap or space between those neurons. And so there's the synapse or synaptic cleft, where we're going to have to communicate with the postsynaptic neuron. Typically, not all the time, but typically this is a chemical communication. And so that's usually what gets discussed. And we're going to discuss still that chemical communication, that now, because I'm feeling that touch, that postsynaptic neuron receives enough information that it also reaches its threshold of excitation and sends its action potential. So what does that mean? To receive enough stimulation or enough excitatory activity. We had just finished looking at a bunch of different, well, we used three examples of neurotransmitters. But so what's happening with those neurotransmitters is they're floating across that synaptic cleft, and then they are affecting the postsynaptic neuron, and they cause what's called a postsynaptic potential. So there's this voltage change at the receptor site because of whatever that neurotransmitter is, right? So they have each have their different effects, although I will say the effects overall are either excitatory or inhibitory. Basically, the brain is using ones and zeros, or ones and negative ones, to say, now does the postsynaptic neuron fire? And we're doing this along these neural networks. So the postsynaptic potential is not all or none in the same way that the action potential is all or none. What it's doing is it's changing the probability that the postsynaptic neuron will fire. So when we say that it's changing the probability that the postsynaptic neuron will fire, it's making it either more likely to fire or less likely to fire. And so how this works is we have excitatory transmitters, or really transmitters that can have an excitatory effect. It really depends on the situation. They're going to cause a depolarization. So if you think about what polarization means, when I'm at zero, I'm not polarized at all. I usually use the example of if we're in agreement, we're not polarized. I don't know how often you've heard that kind of terminology for having an argument or being away from each other, but the farther away we are, the more polarized. And the same thing we see. So we looked at that resting potential. I have it as negative 70 millivolts. That's from the textbook. It's pretty typical for neurons, but they do vary. And so you'll see other estimates out there. You don't need to know the negative 70 millivolts exactly. So some of them say negative 65 or negative 60 millivolts. So we're going to depolarize that. We're going to take away some of that polarization. As we get this excitatory information in there, we're bringing that potential, that voltage, up closer to zero and up closer to this threshold of excitation. Okay, so if you see the dashed line on the figure, that's my threshold. So I'm bringing it up closer to that threshold of excitation. So an excitatory transmitter is going to make the postsynaptic neuron more likely to fire. We also have inhibitory transmitters, or cases where a neurotransmitter or a neurochemical has an inhibitory effect on the postsynaptic neuron. And this means it's hyperpolarizing. So hyperpolarizing is causing it to be even more polarized. So making the postsynaptic neuron less likely to fire. And these transmitters can prevent postsynaptic neurons from generating their action potential, or make them less likely to fire. And some of probably the best example of an inhibitory neurotransmitter that gets talked about is GABA, or gamma aminobutyric acid. This is what is in things that help us sleep, those Valium type drugs that help us to calm down. They're basically giving some balance back to the nervous system of causing those neurons or making those neurons less likely to fire. And then these postsynaptic potentials, these PSPs, they add up. And so we're adding up positive ones and negative ones, basically, to see, do I reach my threshold of excitation? And this is done in a process called neural integration, that we're integrating those potentially thousands of signals, right, that are excitatory and inhibitory, and seeing, do I reach this threshold of excitation? Do I send an action potential? And typically, a neuron is receiving both excitatory and inhibitory signals. So when I say enough stimulation, it is enough excitation given the inhibition such that I still reach my threshold of excitation. That's what's important, is that I reach that threshold and then I send the action potential. And what this picture is really showing is the depolarization, the hyperpolarization, that and then the figure on the right, that dashed line, that threshold of excitation. I get enough excitation that I reach that threshold, and we see that massive depolarization, as they call it, that massive depolarization going up to positive 40 millivolts. That's happening because of the fact that we're sending an action potential, right? We're opening those sodium channels, sodium rushes in, we go up to positive 40 millivolts, we close the sodium channels, potassium's coming out, and then we come back down to negative 70 millivolts. Or actually we overshoot slightly. Talking about some basics, some very basics of the physiology and how the nervous system works. And now we're going to take that into the eye. And I'm going to do something here that I'm going to end up repeating. And it might feel like a lot of repeat to some of you, and you might just skip by if you're noticing that the slides are similar and you know and understand. But for most of you, you'll want to hear it a second time. I usually do a lot of writing on the board at this time, and it's some complicated concepts here. So if we're looking at this wiring, remember it's usually not a single neuron to another single neuron. It sometimes is, but more often than not, it's many neurons communicating to a single neuron, right? And we're going to go through these neural networks. If we look at what's happening in the eye, so at the back of the eye, we have the retina, and we have rods, and we have cones. They are our sensory receptors, our photoreceptors. The rods and cones allow us to take that electromagnetic information and turn it into action potentials, or electrochemical information that the brain can understand. If we look at the cones, and we look at the cones in the fovea, so those foveal cones, and if you want to think about this way, so look at something that has writing on it. And if I look over at this cookbook that I have and it has the writing on it, I look at it and I look at the writing and I get this really good resolution or high acuity because I'm pointing my eyes at it, right? Because it's on my fovea. If I even move down to another bunch of words on the cookbook, those other words, they're now a little bit in the periphery and I can't read them anymore, right? They're not as clear and crisp. So the reason this is happening is because of the foveal cones, and it's really because of the circuitry of those cones. If we look at these circuits that are created along these neural networks, this linear circuit for the foveal cones means that each of those cones, if we have a one-to-one circuit, each of those cones is represented in the brain, and it gives us this high acuity. When we move out of the fovea and we go into the periphery of the retina, we have convergence. With the cones, that convergence is 6-to-1. We have fewer cones than we do rods, and they're converging onto these retinal ganglion cells that are going to send that information to the brain. But their convergence is 6-to-1, whereas the rods' convergence is about 120-to-1. So you can see they're not getting the same kind of representation in the brain. I'm hearing from a lot of rods, and a single neuron is going to communicate. What do I hear from these 120? If you imagine people whispering to you or shouting at you or whatever, you can't tell the voices, right? If there's a single voice, I hear it. If there's 120 voices, I don't hear the single voice anymore. I just hear this kind of voice, this noise. So for the convergence, we have what's called spatial summation, because these are cross space on the retina, and that spatial summation, that's because of that happens because of that convergence onto a single neuron, gives us increased sensitivity. Where what I mean by sensitivity is sensitivity to dim light or to low light levels, but we decrease the resolution. We have a low acuity. And here we see a picture that is showing us the retina, where the very top of the picture is the very back of the retina, and those are our rods and cones. You can see some are a little bit more rod-like, some look a little bit more like cones, and those are the outer segments that you can really see there in orange. They're doing the transduction, and then sending that information through vertically through bipolar cells to the retinal ganglion cells, or what here are called ganglion cells, but they are ganglion cells in the retina. So they are retinal ganglion cells, and you can see that those dark orange neurons at the bottom, and they're sending their axons, and they're all cabling up. Their axons are going to make up the optic nerve that we're going to be talking about. And then we also do see that there are signals that are sent horizontally, which for right now we're gonna ignore those for a little bit, and then we're gonna come back to them. So between the receptors, we have horizontal cells that are sending information horizontally or perpendicularly to the rest of the communication, and then between the bipolar and ganglion cells, there we also have another set of cells called amacrine cells that are sending information horizontally, or really perpendicularly to the communication that's happening to get this out of the eye, this information out of the eye and to the brain. Cross section of a monkey retina, the little purple dots. The dots are the cell bodies. Kind of just cool to see. Maybe not you, but I think it's very neat. Okay, so looking at the rods and the cones, where the rods, we're going to look at them on top in A, and cones, we're looking at those on bottom at B. And it's this diagram is trying to show you, right, that those rods, we have 5 rods here converging onto one bipolar cell. I'm going to call that red dot the bipolar cell, just because that would be the next one in the line, and that's what we're looking at here. And what this is showing, right, is that convergence, whereas down in B with the cones, each of those cones has their linear circuit, right? So each of those cones communicates to a single bipolar cell. So if what we're doing is, so we're in a, let's say we're in a dim light, and I'm a bipolar cell, and I need 4 units of activation to fire. And I'm in a dim light, and so each of those rods is receiving 2 units of activation. And I'm just going to label the rods and cones, so 1 through 5, 1, 2, 3, 4, 5, moving from left to right. In the diagram on your left in A, right, I'm getting 2 rods being stimulated, so I get 2 4 units of activation, and the bipolar cell fires. But one of the things you can see here is if I move those lights around, and instead of hitting 4 and 5, I'm hitting rods 3 and 5. Right now I have 2 separate lights that are separated from each other with space in between. What happens at the bipolar cell? It gets its 2 4 units of activation. It fires in the same exact way, right, as when it got when 4 and 5 were being stimulated. And so it's losing that acuity. Where are those lights? I'm not sure. I just know that there's some light out there over that direction. If we look at what's happening with the cones, and if what I need is 4 units of activation to fire, then and I get 2 units, I'm in this dim light, I'm getting those 2 units from cones 4 and 5. 2 units, I don't fire. 2 units, I don't fire. So those cones, they don't have that sensitivity to dim light, and they just don't see it. Same if I'm hitting those 2 dim lights or hitting 3 and 5, right? I just don't see that light because I'm not receiving enough activation. So let's turn those lights up. We're going to turn those lights up so that we're at 4 units of activation for firing. If we look at what's happening with the rods, we have the same situation, 4 and 5. I'm getting 8 units of activation. I'm firing. How am I communicating signal strength? I'm going to fire faster. I get 3 and 5. I get 8 units of activation. I'm firing faster, but again, I know I'm in brighter light, but I don't know where those lights are. I've lost the acuity. I take those down to the cones. I get cones 4 and 5. Give each of these bipolar cells their 4 units of activation, and each of those bipolar cells fires, and they tell me over there at cones 4 and 5, we have light out there. And if I spread that light out so that it's hitting, I have 2 separate lights and they're hitting 3 and 5, what I'm going to see represented in the brain, right, is that this bipolar cell 1, I don't see any light. 2, I don't see any light. 3, that bipolar cell, that's telling me that there's light right there. 4 is telling me there's not light here. And then 5 is telling me there's a light here. So I can see now that where that information is coming from more precisely. And I can see and distinguish, right, when there's some space between them. And so I'm getting that high acuity. But if I go back down into the dim light, I'm just not going to see it. And so now measuring from bipolar cell B, that specific bipolar cell, I look at a simple circuit. I have a dot of light out there. It's hitting receptor 4. It's a relatively dim light. It's about a unit of 1. So B is going to fire at a unit of 1, or at a rate of 1. I take that bar out farther, and so that it's a bar of light that's hitting receptors 3 through 5. But B is really only being influenced by receptor 4, and so I'm going to stay firing at 1. I can make that bar of light longer, 2 through 6. I, as B, I'm still just going to fire at a rate of 1, and I can make that bar of light even longer, hitting cones 1 through 7. Here at B, I'm still just being influenced by receptor 4. I'm still going to fire at a rate of 1. But we're going to make this more complex. In a more complex circuit where we have bipolar cells communicating horizontally or perpendicularly, so they're communicating to each other, and also receptors communicating in a more convergent kind of way. Now I have my dot of light up there. It's hitting receptor 4 at a unit of 1, and B fires at a rate of 1. I take that bar of light out farther, so it's a bar of light, it's hitting 3 through 5. Now B is firing at a rate of 3. Take that bar out longer, so it's a light that's hitting cells 2 through 6. Now I'm going to fire at a rate of 5. And then if I take that bar out even farther to hit 1 through 7, B is going to fire at a rate of 7. So this allows for that convergence. Those little Y's at the end are showing, or those little lines at the end that are hitting each bipolar cell are showing that this is just excitatory information. And this convergence allows me to see in dimmer light, right? I can bring that light level down, and B can still reach its threshold of excitation. But what we're actually going to see in a sensory system, which is really important for a sensory system, is to not just have convergence, but to have some inhibition. And I've thought of different ways to explain why we have this lateral inhibition. So again, communicating perpendicularly or laterally in the circuitry. And I think of it now as, if you think about hearing those 120 voices. So in order to hear a voice, they don't all need to just scream louder, right? They need to talk louder, but they also need to shush their neighbors and the people around them. And you can think of this as the same with getting attention as a kid from your parents, right? If you have 5 or 6 kids in your family and you're all making noise, nobody really gets the attention because everybody's getting the attention has to be spread apart. And what I want is that attention. And so what I really need to be able to do is to kind of hush my brothers and sisters and talk louder than them. But part of it is hushing them. Okay, so we're going to see this. I'm a dot of light. I'm hitting receptor 4, and you can see the excitatory little Y. Now the inhibitory, those little just single lines that are across, those are inhibitory synapses. So I'm a dot of light. I'm hitting receptor 4. It has an excitatory influence on B. It's at a rate of 1. B is firing at a rate of 1. I take that bar of light out. It's hitting 3 through 5. They all have excitatory synapses with B, and they all are getting that light is that it's giving me 1 unit, and so now B is firing at a rate of 3. Take that bar of light out farther to 2 through 6, and now 2 going through bipolar cell A is giving inhibitory information to B. 6 communicating to bipolar cell C is giving inhibitory information to B, and so now I've gone up to 3, and then I've subtracted 2, so B is now firing at a rate of 1. And I can take that bar of light out farther, hit through 1 through 7, and because 1 and 2 and 6 and 7 are both sending, all of those are sending inhibitory information, I'm going to slow that down to under 1, and actually I'm most likely going to inhibit B from its spontaneous firing, from the fact that it just fires every once in a while, right? So I'm inhibiting B. And what you can see here is one thing, B, that particular neuron, it cannot tell the difference between a dot of light at 4 and a bar of light that's hitting 2 through 6. That's the same exact level of light. And as we get out through 1 through 7, it gets a little bit more complicated of what B is experiencing. So it's not getting that acuity. We have this convergence, and we have some inhibition. And this will become important. Just kind of put this away in your mind that we have these excitatory and inhibitory influences on neurons. That's what we do in the nervous system.